Mass spectrometry, analyzing the M+1 peak. So, here's our molecular ion peak at M/Z equals 16. That's for a normal methane with a carbon 12 and 3 normal hydrogens. But we also see this tiny peak at M/Z equals 17. That's our M+1 peak. And why do we see that? Well, one thing, it's important to take note of the relative abundance. Here the M+1 peak is only about 1% of the abundance of the molecular ion peak. It turns out that the M+1 peak results from the presence of carbon 13. So 1.1% of all carbon atoms are carbon 13. That means that if you had 100 methane molecules, 99 of them would be carbon 12, and that would show up as this peak, the molecular ion peak. But one of them would be carbon 13, and that's why you'd see this peak here. And that explains the relative abundance. The abundance of the M+1 peak, usually, is equal to the number of carbon atoms times 0.011 for that 1.1% times the abundance of the M+ peak. So here we've got 1 carbon times 0.011 times 100, which equals 1.1. But we can also rearrange this equation to find the number of carbons. So the number of carbons equals the abundance of the M+1 peak over 0.011 times the abundance of the molecular ion peak. So if we take the abundance of our M+1 peak and we divide it by 0.011 times the abundance of the molecular ion peak, we get the number of carbons. Sometimes you'll see an M+1 peak that's even bigger. The more carbon atoms are in a sample, the more chances there are to have carbon 13, so the larger our M+1 peak will be. So, the height of our M+1 peak is about 11. Divide that by 0.011 times the abundance of the M+ peak, which looks like it's about 99. And we get 10.18, or 10.01, right? Which means we have 10 carbons here, which makes sense because this is decane. Here's an exercise for you to try. What's the molecular formula based on the following mass spec data? We've got a molecular ion peak at 132 with a relative abundance of 38.3, and we've got an M+1 peak at 133 with a relative abundance of 2.95. Pause your video and work it out. So the first thing we want to do is figure out how many carbons there are. And we take the percent abundance of the M+1 peak, which is 2.95. We divide it by 0.011 times 38.3, which is the percent abundance of the molecular ion peak. Which gives us 7 carbon atoms. So if we have 7 carbon atoms, 7 times 12 equals 84, and 132 minus 84 is 48. We could get 48 with 2 oxygens and 16 hydrogens. So, C7H16O2. Nice job. Nitrogen can also have an effect on the height of the M+1 peak. 99% of all nitrogen is nitrogen-14, but 0.37% is nitrogen-15. This means the presence of nitrogen can add to the height of your M+1 peak. And so, the abundance of M+1 actually equals 0.011 times the number of carbons times the abundance of the molecular ion peak plus 0.0037 times the number of nitrogens times the abundance of the M+ peak. You will see this illustrated in practice problem 1453 from problem set 4C.